Hi, Steve Hughes. Outside the University of Queensland bike shop, the Uni bike shop you can see behind me. And today I want to discuss just how circular the orbits of the planets are. So for example, the Earth going around the Sun, and often in textbooks it looks like the orbit of the Earth around the Sun is very elliptical, oval shape, but actually it's very close to circular. So we're going to look at an analogy with bike wheels to demonstrate that. So here we've got a bike tyre which represents the orbit of the Earth, so it's sort of nice and circular, but in textbooks often what we see is the orbit which is highly elliptical. So I'll just push this in here like that, and the Sun is say like there, and then we've got the Earth going around the Sun like that. And that gives the impression that the Earth is much closer to the Sun during the summer, which is actually true here in the Southern Hemisphere in Australia. So the Earth is actually 5 million kilometres closer to the Sun during the summer than it is in the winter, which would be over there. But of course, the opposite is true for the Northern Hemisphere. At the moment, it's winter in the Northern Hemisphere, and the Sun and the Earth are at their closest point. Now, the reason why the orbit's drawn like that in textbooks, one reason is to exaggerate the orbit, so it looks like an ellipse, to explain Kepler's 3 planetary laws, the first of which is the planets don't go around the Sun in perfect circles, as the ancient Greeks believed, and also to show that when the Earth goes around the Sun or any other planet, if you join the center of the planet to the Sun, that line sweeps out equal area in equal time. I call it pizza physics or pizza mathematics. If you imagine if you've got a large pizza, you can have a narrow wedge of a large pizza, and that can be the same area, the same size as a wide wedge from a small pizza. So it's like that. And so in order to be able to see that quite clearly in a textbooks, like all the textbooks in the library here at the university, then it's necessary to actually draw the orbit as an ellipse. And also often orbits are drawn like that in textbooks, where you've got the Sun there in the middle, and then you've got the Earth at different positions at the equinoxes and the solstices, and the view is like as if the orbit is actually twisted like that, oblique. So the writers of the textbooks, they know that the orbit of the Earth is pretty circular, but it's drawn obliquely, but that gives the false impression that the Earth's orbit is far more elliptical than it actually is. In fact, when we sort of compare the orbit of the Earth, for example, with a 26-inch bike wheel, the actual deviation from a perfect circle is less than 0.1 of a millimetre. So probably about the thickness of thin paint on a bike. And even the orbit of Mars, that's like a bike wheel which is out of tolerance by 2 to 3 millimetres. And I suspect a lot of bike wheels are not as good as that. Neptune and Venus are very close to perfect circles. Mercury is the least perfect orbit. It's out by about 14 millimetres. But I think even 14 millimetres on a 26-inch bike wheel, that wouldn't be too bad. You would still go along on the bike. Now, the largest influence on the seasons is not the distance between the Earth and the Sun, but the tilt of the Earth relative to the plane of the Earth's orbit around the Sun, a 23.4 degree tilt. So this is a situation here in the summer, which is now, where the sun is high in the sky, so the rays of the sun are concentrated on the Earth, producing more heating. Then 6 months later, during the winter, we're like that, where we're tilted over the other way, and so you see Australia sort of lower down, and that means the sun is lower in the sky, and the rays of the sun are spread out over a greater area, so there's not so much heating. Hi Gavin, so we're Gavin Young of the bike shop, Uni Bike Shop, and can you just explain what this thing is, please?
Okay, basically what we use this for is to true wheels up, which means we need to get the wheels very, very precise.
Yeah.
Within a millimetre.
Yeah.
Of tolerance within the balance of the wheel.
Oh, great! Yeah. Yeah.
So that's important because balancing a wheel, truing a wheel,
Yeah.
really important. The higher the speed,
Yeah.
it will increase the speed wobble.
Yeah.
So
Yeah.
that's really important to get that part right as well.
Yeah. Yeah.
Tension on the spokes is
Yeah.
what determines which direction the rim
Okay.
will move.
Yeah. Yeah.
And you actually physically loosen and tighten spokes.
Okay.
You don't just
Get it.
reef up on one side of the spoke.
Okay.
Because otherwise what will happen is it'll pull a bump into the wheel and the wheel
Okay.
will move up and down, and that'll even create more of a drama.
Yeah. So people, when you're driving, well, riding along, it's all going up and down,
Absolutely,
like
yeah, up and down, yeah,
on
yeah.
a simulated rough road
The
type thing.
tyre will take up some of that,
Okay.
but at a higher speed it
Okay.
obviously will create
Yeah,
a bit of a
yeah.
a wobble. Yeah.
So with the Earth's orbit, less than 0.1 millimetre deviation over 26 inches, that would be pretty much a perfect bike wheel if you could
Perfect
get it
bike
that
wheel,
way.
Yeah, absolutely, yeah.
Yeah. So even like Mars, let's say like 2 to 3 millimetres
3 mil,
out.
yeah.
So you could ride a wheel like that.
It would be
But-
tolerable, yeah.
Tolerable,
but
okay.
Obviously, the higher the speed,
Yeah.
the more chance there is of creating.
Oh, okay.
friction.
Yeah.
So
Yeah. So what's this? How many mil?
This one now is 14 millimeters out.
Okay, it's interesting because that's about the same as the orbit of Mercury. So if Mercury was a 26-inch bike wheel, then it would be out by about 14 millimeters. So that would be an interesting experience riding a bike with a wheel out by 14 mil.
Oh yeah.
It would.
Yeah, it
Okay.
would, yeah, absolutely.
Yeah.
It'd be probably a bit uncomfortable too.
Yeah. Oh, great. No, thanks for that. So this is the same bike wheel that Gavin has just showed us. It's on the touring stand, it's rotating around, and I've taken the video using slow-mo, and you can see the wheel wobbling from side to side and maybe going up and down a little bit. This wheel is out by 14 millimeters, and so if the orbit of Mercury was modelled as a bike wheel, 26-inch bike wheel, this is what it would be like. Now the model of the bike wheel is not quite accurate because the orbits of the planets don't wobble up and down. They're only sideways motion, essentially as if they're on a flat sheet of paper. Now earlier I mentioned that the ancient Greeks believed that the orbit of the planets were perfect circles. In fact, they believed everything in the heavens had to orbit according to a perfect circle. Now, paradoxically, that's actually closer to the truth from what many people believe and what is shown in the textbooks. And so if you'll excuse the deliberate pun, we've now come full circle.